All right. Not much of a pregame today. I we got 5 minutes left here. As you can see, we're moving along quite well. Excited for day 5. I think the challenges are going to get up there, start to ramp up. So far, we've done pretty good. Let's see here. So I did make a couple of changes to my day 4. I'll just kind of review those real quick. I moved some of the directions to the matrix package so that if we have all directions or X patterns, we can kind of just reference them. I have some ideas to optimize this more, but I'll do that at a later time. Right now, the focus, of course, is day 5, so we'll stay focused on that. But we're all set up. I can run day 5. Oh, I forgot one thing. Yeah, there we go. Yeah. And then we can test from right here instead, so we can get an idea of what our output is. Right. So, close that. All right. We are good to go. 2 minutes and 46 seconds. Hmm. While we look at that, let's look at our stats here. So this is interesting. You can kind of see how many people have kept up, completed first, second, third, and fourth day. The number seems to be dwindling. Watch my videos, people. Right. One minute and 13 seconds. So I've been using LLMs to generate the video descriptions for me. I take the input of the output of the day after I'm completed, and then I add some more context to it, and then I ask for it to provide a 3 to 5 sentence YouTube summary. What do we think this is? Usually this draws some sort of picture. Sometimes it's animated, sometimes it's not, but I've seen also where like things change. It almost looks like this is a little bit of a Christmas tree here, but I'm not 100% sure. It's kind of like revealing itself as we go, and wondering if it might change day to day. I remember last year, there was like a lava pouring down at one point. All right, 3, 2, 1. All right, let's take a look. Day 5, print queue. Satisfied with their search on Ceres, the squadron of scholars suggests subsequently scanning the stationary stack of sub-basement 17. The North Pole printing department is busier than ever this close to Christmas. And while the historians continue their search of this historically significant facility, an elf operating a very similar printer beckons you over. The elf must recognize you because they waste no time explaining that the new sleigh launch safety manual updates won't print correctly. Failure to update the safety manual would be dire indeed, so you offer your services. Safety protocol clearly indicates that the new page for the safety manual must be printed in a very specific order. The notation X pipe Y means that if both page number X and page number Y are to be produced as part of an update, page number X must be printed at some point before page number Y. The elf has for you both the page ordering rules and the pages to produce in each update. You're a puzzle input, but can't figure out where each update has the pages in the right order. For example, 47, 53. The first section specifies the page ordering rules, 1 per line. The first rule 47, pipe 53, means that if an update includes both page number 47 and page number 53, then page number 47 must be printed at some point before page number 53. 47 doesn't necessarily need to be immediately before 53. Other pages are allowed to be between them. The second section specifies the page number of each update. Because most safety manuals are different, the pages needed in the updates are different too. The first update, 75, 47, 61, 53, 29, means that the update consists of page number 75, 47, 61, 53, and 29. To get the printer going as soon as possible, start by identifying which updates are already in the right order. In the above example, the first update, 75, 47, 61, 53, 29, is in the right order. 75 is correctly first because there are rules that put each other page after it. 47 is correctly second because 75 must be before it, and every other page must be after it according to 47 is correctly in the middle because 75 and 47 are before it. 47, 61, 53, and 29 are after it. Because the first update does not include some page numbers, the ordering rules involving those missing page numbers are ignored. The second and third updates are also in the correct order according to, also in correct order according to the rules. Like the first update, they also do not include every page number, and so only some of the ordering rules apply. Within each update, the ordering rules that involve missing page numbers are not used. The fourth update is not in the correct order. It would print 75 before 97, which violates the rules. The fifth update, 61, 13, 29, is also not in the correct order since it breaks the rules 29, 13. The last update is not in the correct order due to breaking several rules. For some reason, the elves also need to know the middle page number of each update being printed. Because you are currently only printing the correctly ordered updates, you will need to find the middle page number of each correctly ordered update. In the above example, the correct order updates are 61, 53, 29. Okay, so that's how we're going to get the score. Of course, you'll need to be careful. The actual list of page ordering rules is bigger and more complicated than the above example. Determine which updates are already in the correct order. What do you get if you add up the middle page numbers from those correctly ordered updates. Okay, so I think I have a pretty good idea of how I want to solve this. So we have a list of rules, and page 47 means that if an update includes both page 47 and page number 53, then page number 47 must be printed at some point before number 53. So we know that if we look here and we grab 75, we find 75 in our list of rules. 75 is in here several times, but one of them is 13. The other one is 47. And we know that if a 75 is going to print, that the page number 47 must be printed at some point before page number 53. So we know that 75 has to come before 47, which is true, and 75 has to come before 13, which is also true. So let's grab our input here. So the way we're going to solve this, I think, just right out of the gate here is with a map. And so what we're going to do is we are going to create a map of key to index value. So 75 would be 0, 47 would be 1, 61 would be 2, 53 would be 3, etc., etc. And then in that, we also have our rule set, which will be a map of key to values that must appear after. And what we can say is, okay, in our map of our key indexes, we can say, okay, where is 13? Does 13 exist? If so, is the index of 13 after the index of 75? I think this will probably be the best way to approach it. And then if it doesn't exist, then we know we're okay because we can ignore those. And then if at any point it's a lower number, then we know that it's not after. And if it's not after, we know that the rule is busted. So the first thing we have to do is parse the file apart into two sections: our rule section and our what are these called? The second section specifies the page number of each update. We'll say rules and updates. So we have a list of updates here, which we can process with our grid, and then we have a list of rules, which are up here. So we can then, okay, that's interesting. So we come here, we can just start by bytes.split. Is that right syntax? This has to be yeah, and then so we've got that, and so now we know that immediately we can create our matrix by doing a matrix.new, and we can pass in items sub 0. Since we know the control, or I'm so sorry, sub 1, since we know our control of what our input is, we can pretty easily we know that our separator is going to be a comma. So if we go back to our test input of our matrix part, those are our commas. And then since we know what our input is, we can be pretty safe. I would normally test for this, but I'm not going to test. We're just going to go ahead and do it. And then so we can say, okay, we want to create for each row or R in range of M, we're going to create a map of, so this should just be simply call it a map of int to int. And so on the left side of that will be the number, so the value, and then on the right side will be the index. So we'll call it p index sub r equal to I. We need to do this as ints because we want an int matrix, right? And these are, yeah, type int, so that's what we want. So then p index sub r, because we actually want to do this for each row. So this needs to be for I, C, range of R, and then this actually becomes that, and this becomes that. So now we have the actual, so for each row, for each number, so like in this case, in our test case, it would be 75. I realize I skipped the rules for a second. We'll come back to that. But 75, 47, 61, that's what we're looking at here. And so we're going to create that unique set. We're basically going to create the index of that slice. Instead of having to go through the slice every time, we can use a map for efficient lookup. And then what we want to do then is we'll go through that once. We'll create the map, and then we'll go through it again. And the rules are going to be a map of ints, which will be our let's look at these rules first. Let's go back and look at our example here. We go back and look at our example. Those rules are 47 is the left side, and then it's a list of ints, because we could have 47 in here more than once, right? So every rule has another int that 47 has to come before. So what we can do is, this is just going to be a map of int to slice of ints. And we'll populate that in a second. But as we go through this slice a second time, right, all we have to do is simply say, yeah, so we can say for yeah, let's see here. I might want to turn this into a function so it's a little bit clearer, but we're going to say if rule for a given character, so rules sub C, right? Actually, I think we can just do, yeah, let's do for sub C. And so what we're saying is, okay, get the rule set, right? And we can say if I I want to just be careful here. Let's just so we're going to go back to p index sub rule. So And then we can do, so that is the other character index, right? And we can say if I is greater than n, that is our not okay condition, right? And we can break. What I don't like, what I think what I want to do is actually create this function called is valid, because it's going to be easier to articulate this in a function like this, where R is a slice of int. Yeah, so we're going to create this is valid function. We can move these in. So I think I want to pass this in here. And then, sorry, this needs to go. I meant for this to go here. And then rules are this. We'll call that row. So R, what else do we have here? Our index and rules. And then this is going to return a bool. And so if this is true, we return false. Otherwise, we return true. And I think that should solve our first test case. Our inputs, based on our input 143. Oh, we got to do one other thing, which is we got to grab the middle number. So let me come to my test case first. I'll just plop this in 143, and then we've got to, so now if we know it is valid, we're not going to grab that. We are, so if it's 5 and we divide it in half, and we're going to take the length of R. Yeah, I think that will do. Okay, so we need to grab that midpoint out. 143, 278. So length of R, if it's 5, I'm now doing 4 divided by 2. And we want the 0, 1, 2, 3, 4. That is correct, right? 143. Let's just log it real quick and just say logRS info f %s is valid, and we'll put R in place there. And let's rerun this. 1, 2, 3, 4, 5, 6. Okay, so all 6 are coming back as valid, and we know that that is wrong. Let's just make sure. How much is in the test input? Why did I get back 6 that are valid? 75, 97, 75. Okay, 3 or 5. Oh, duh, I didn't parse the rules. Okay. I gotta parse out the rules real quick, and then we're done. So for the rules, actually, I'm actually gonna load those as a grid as well, just to make this, or and what we can do is we change this to position 0, and we change this to a pipe. And now for our rules, we can say for and then we can say we only know that there's 2 values, so we don't have to be super complex here. We can say for rules sub 0, or R sub 0 equal to append that same thing, but we're going to append R sub 1. Yeah, so we're going to append the rule based on the key, and we're going to append all the things that must come after it. So now, there we go, test pass. So if we grab our input, and we come back here, and we put that into 1.txt, and we run, score part 1 is 41.35. I don't know why that second part is panicking. We'll look at that in a second, maybe. But 41.35, so let's put this in here. That's right, awesome. Part 1 is solved. Part 2, while the elves get to work printing the correctly ordered updates, you have a little time to fix the rest of them. For each of the incorrectly ordered updates, use the page ordering rules to put the page numbers in the right order. For the above example, here are the 3 incorrectly ordered updates and their correct orderings. After taking only the incorrectly ordered updates and ordering them correctly, their middle page numbers are 47, 29, 47. Adding these together produce 123. Taking only the incorrectly updated, find the updates which are not in the correct order. What do you get if you add up the middle page numbers after correctly ordering just those updates? Okay. Interesting. Right. Okay, so we have a mechanism to determine what is correct and incorrect. Oh, I know. I think part two failed. So we have a mechanism to determine if they're valid, and now only if they're not valid do we want to reorder them. So I'm actually just going to copy part one here. I'm just going to copy part one into part two. And I'm just simply going to say not valid. And then we have to somehow reorder them. So let's look at this in a different way. How can we reorder this efficiently? Well, 61, 13, 29. If we build a set of numbers, if we know what our set of numbers is, I can then use that. So if I start at 61, I can determine it. Okay, if we look at our list of rules, is 61 in here? 61 is 29. And we can say, okay, is it correctly ordered at 61? Yes. Is it correctly ordered at 13? If no, swap the number. And I think we can just keep swapping them moving forward. And in theory, it should eventually order, but how many times would I have to do a pass? Because we could be inadvertently putting other things out of order. I think that's kind of like the brute force approach, but eventually, if we do that enough passes, we should get it in order. So So if we use this, we'll just rename this to in, and then we'll keep rewriting in. Yeah. And then eventually that should be true. So then swap invalid. Yeah, so swap invalid says if I is less than n, then r sub I R sub n equals to R sub n R sub I. And we're just swapping the two. And we're going to move forward and keep doing that. Okay. And then 123 is the invalid. So cleared and not used. RI. Oh, that's because it's up here. Yeah, I ended up not using this. Let's see here. What am I doing wrong? Because the index is changing after each one. So I have to recalculate the index. Otherwise, it's just reswapping what is supposedly the same characters over and over again. And then I also need to do it based on in, not R anymore. So let's see here. I just want to see if I can understand what's going on with the swapping. It feels like this is not swapping properly. I am rewriting the index every time. The rules aren't changing. Oh, I think I understand what I'm doing wrong. Um, 97, 29, 75. Okay, that approach isn't gonna work. Um, it's because it is constantly recycling 97, 29, 75, 47, 13. We're kind of getting into this loop where it is swapping, but it is swapping in such a way that it keeps recursively getting back to the same invalid input. So it's good we found that in the test. But okay, so let's think about this a little bit differently. If we have our index of characters, swap invalid. One second. Just simply swapping them is not going to work. That is evident here. So we have to be a little bit smarter about how we approach the swap, or how we realign them. So the other thing I'm thinking of is we have the rules which can kind of help us build a tree of characters, and we can use that rule. I think we can leverage that rule to determine if we have in our index, we could just start by placing one value, and then we take the next one, and we look to see if any of the rules apply. Can we place that value afterwards? Maybe. Hmm. And then you kind of treat it like a kind of like a node problem, in a way, where we're traversing a tree. Um, and then anytime we can create the rules both ways. Um, maybe that would be a more optimal way of doing it. I wonder if there is a deterministic answer with the rules. Um, hmm. see what we can do here. Right. So if we've got our list of numbers, call it this here, we'll try to visualize this. Actually, let's look at the one in the output. Yeah, 97. This last one here is the one that kind of hosed us up. So if we put this in our output, let's go with black, and we'll create this to be like 96. And we'll put it like that. And we know that potentially this could be completely out of order, or it could be in some segment of order. So what I think we can do is if we just simply create a new list, and we create we have the rules, and we take 97 and we place that in the list at this location, 97. And at the same time in this list, we create a map of the index, or we know what the index is. Then we move on to 13, and we check to see if the rules for 13, so if we go and we look for 13, so 97 must come before 13. So if we have a 97, but we don't care about that, we care about the 13. So we can reverse that rule set, and we know that if we have a 13, we can look in here to say, do we have a 97? If the answer is yes, we know that the index must come after, otherwise it can come before, but it can't in this case. So we put this here, we put 13 in this location. Okay, now we go to 75, and we have rules for 75. We know that one of them is 7529, 7561, 7513. Here's 13 again. But really, we know that '75 must come before 13. So I guess we can use the same list. And so we need to check and say, okay, is 75, if we go back here, is it in our rule set? Do we have a requirement for 97? No. Do we have a requirement for 13? Yes. Okay, it has to come before 13, so we have to insert it one index before. And I think then this becomes 97, 75, 13. And then we do the same for 29. What are the rule requirements for being previous to? And we insert that one, and so on and so forth. And we do it based on the earliest one in the list. The problem is, yeah, because if we do it based on the earliest, then we always know it's going to go earlier in the list here. Well, I don't know if 29 should be earlier, but we get the point. So on and so forth. I think that's how we want to do it. So let me take this another approach here, and let's try this. So if we come back and we say, okay, we'll call it new. It's a slice of ints. Yeah, it's whatever. Call it out. And for each C, we really need to I'm just going to create a function for this real quick because it will just help me. And the in is a slice of int. And so we can ignore that for a second. So we want to, each time we iterate through for a new character, we want to get an index of out do I care about the index of out? Do I care? Get rid of this for a second. Why do I care? Because okay, so if I is greater than n, I think I still have something kind of off here. Yeah, so let me take that out for a second. We're going to call insert into 0. So we always insert at the beginning. And the rules, man, I'm getting myself wrapped here. 47 means that if an update includes both page 47 and page 53, then page 47 must be printed at some point before 53. Okay. So if we have a letter n, then we want of the R index rule, then we need to, if that letter exists, that is at position n, and that is the beginning. So then our insert needs to be n plus 1. And then, okay, hold on. I think I might, my brain is working a little bit faster here. Okay, so, right, right. I feel like this is very inefficient, but I think it might work. So our insert index is going to be 0 always. We're going to start at the beginning. We're going to iterate through our rules, and for each rule where we have a character match in our list, we're going to set the insert to the index +1, and then we're going to insert it into our slice at the very end. So let's try this out and see what we get here. Yeah, we don't need to pass that in anymore. I don't know if it actually makes sense to iterate on the invalid, but slice out of bounds. Okay. So in our insert, so out is going to equal slice.insert. I don't think that's our actual problem though. So we're inserting at position 75, which is not what we want to do. Insert V. We had these flipped. All right, something's still not quite right here. I see. I see the problem. So what I'm not doing is I'm not insert's okay as long as so we're trying to iterate through this admin of code problem. So what we have here is in this first list, I already solved part 1. We have a set of rules and a set of prints. And the rules are that if we have 4753, we have to have 47 must come before 53 in this list, and that makes it valid. So part 1 was just finding all of the valid ones. Part 2 is for those that are invalid, make them valid, right? So swap them so that they're appropriately valid. And so what I'm doing now is I'm looping through. So like this one is invalid, 97, 13, 75, 28, 47. I'm trying to create it in the correct order. And so I'm attempting to do that by checking to see if we have a rule. And then I actually think it needs to be if similar to what invalid is, which is if I is greater than n, then we swap those values. And so, and this becomes I again, and then it's already run too long. Should be pretty quick. Yeah. 53, 61, 75. Is that how it's initially laid out? No, it's not. Oh, I see. That was the problem. I was grabbing I of the rule, not of the row. So we put this back to 0 and see if that fixes my problem here. If I is greater than n, well, we don't want, okay, hold on. I don't care about this, actually. So that's part of the problem. Our index this needs to be okay. We have a rule, which is a character that is in our index, and our index of that rule gives us back a value of n, which is that character's current index. And if it exists, our index for the rules for that character. So if we have a rule of 75 and that character exists in that index, we want to insert it at n. Okay. And n is the current location. So either it's going to be n or n minus 1. Insert oof, a little bit on the struggle bus here. No, we don't need this anymore. Let me just get rid of that. And well, $13.75, $29.47. Why is 97 all the way on the right? What's the rules for 97 in our test input? So it should be okay, wait, I took something out and I think it should have stayed in there. Just because it already exists. Is that what I'm missing? It's something like this. I'm just not seeing it. Okay. $20. $27.27. Okay, so why is 97 getting moved? That I don't understand. So, oh, okay, actually I do understand. So if it's length, okay, wait. Length of out. Our insert position should be length of out. Yes, okay. So we always need our insert to be at the end. So we're always pushing forward. Okay. That was brutal-ish. Let's see what we got. That's right. Awesome. Okay. Day 5 complete. Jeesh. All right. Let's talk about what I did right. Initially I tried to just let's talk about each solution first. Get rid of this and this, and let's simplify this and this and this. I'll clean this up just a tidbit here in a minute. But 5285 is my second answer, and it is still my second answer. Okay. Let me get rid of some of the logging, and we will talk about the solution real quick. So part one was pretty easy, pretty straightforward. If we go back to our problem here, we have a set of rules, and the rules are if there is a 47, 53 is allowed in the list, but 53 has to come after 47. And you'll find that a number in this rule set is in here multiple times. So you can have 47 and 53, 47 and 13 in your list of prints, but 47 must proceed 53 and 13. And so we just had to loop through that list. If we come back to this example here, and let me erase some of this. So we had to check. Let's use a short example, 75, 29, 13. Okay, I don't know why it chose to do that, but it did. Let's go big. And then what I'm going to do is, let me see if I can echo. What I'm going to do is extract just the rules that matter, so we can look at them here above. And we can kind of correlate them, right? So 75, that was a cheap, poor means way of doing it, but 29 and 13. So because I added the pipe there, we're only getting the rules on the left side. Okay. So here are all of our rules. So if we expand this also to 72, let's make it a little bit smaller, and we'll color it, I don't know, red. Okay. So these are our rules. So based on this, if we look at this list, the way we determine if it's valid is we go to the first character, first value of 75. Let's go actually with, 75. And what we want to know is, can 75 be in this position? The way we know that is we look at the rules for 75 and we say, okay, is there any character, any number after it, or before it rather? So it has an index less. And so we check 29, 53. Well, 75 can't have one before it because it's the first one in the index. So that one is good to go. So then we go to the next one, 29, and we look and see that the only rule is that if we can have a 13, but it must come after. Well, again, there's no other rule here, but we can also see the only rule for 29 is that 75 must come before it. And so we know that that is valid. And then we do the same thing for 13. 13 doesn't have any rules, so it can show up anywhere in the list. So that was part one, and that was pretty easy. We accomplished that by creating a map. Maybe not the most efficient way, but actually I created a function for this. So I can actually replace that, and actually we can probably replace this with that and reduce that down further. But what I'm essentially doing is I'm taking that input slice and I'm creating an index of, or a map of all of the R values, or the values in it, and I'm getting the index position of the slice. So that basically I have an index and I can do quick lookups. And then I created this isValid function that simply looks through the slice, says, do I have any rules that apply? And are any of those characters, where are they at in the rule set? And if the checked value for the rule is less than the index that we're on of the range, then we know that we have a problem and we return false. Otherwise, we end up returning true. And that's how we check the valid bits. That's for part 1. For part 2, it got a little bit crazier because we would end up with an invalid string. So to give you an example, we can look at 61, 13, 29. And if we go back to this example here, why it keeps doing that, I don't know. And we know 13, we know 29, we need the rules for 61. So let me just grab those rules for 61 real quick. We can put those in here. I'll just replace the 29s with those rules, and then we can erase real quick. And so similarly, when we have a 13, well, let's start with 61. We need to make sure that if we have a 61, that there are no characters that come before it. Since it's at the beginning of an index, that's not a problem. So we move on to 13, and we know that if we have a 13, we must have a 61 that precedes it. And so you can see that here, right? So the rule is if we have a 61, a 13, a 61 must come before it, which is true. And then if we have a 29, we know that if we have a 29, 13 rather, it's allowed, but only after a 29. And so that is the invalid input, but the valid input is this right here. Again, with the defaults. Yeah, so if we look down here at this second set of input, we can see the reason this was invalid is because we had a 13 that came before 29. So this rule right here is what made this an invalid slice. So the way that I solved this was we essentially created, I kind of already spoiled the answer below, but I created a new slice, and what I did was I grabbed the value from the, here, I'll erase these real quick. I grabbed the first value, pretend I have a empty slice here, and I move that first one down because there's nothing in this set. 61 goes down. Then I move my pointer to the 13, and I say, is there any rule in here or any value in here that requires the 13 to be preceding it? If not, the index is going to go to the next one available, which is here, and we place the 13 here. And then once we resolve those two, on the last one here, the 29, the index by default gets set here, and then I check, are there any others in this list, which 61 is not. 13, if there's a rule for any of these previous ones where they're indexed, 13, and I say if that index is less than my current insertion point, move my index here and insert it, which gives you 61, 29, 13. And that's how we solve the problem. I did go through a brute force tactic before this final solution that did not work, and that was just a terrible idea anyway. So we'll not talk about that, and that wasted a little bit of time. But that is essentially the route I took. Could we clean this up any further? Probably. But maybe not. Maybe the question we could talk about is, instead of just an is valid, which is returning true or false, maybe we could return the index. Maybe we could do something a little bit more optimal where instead of recreating it, we tried to swap some values. But then what I ran into is swapping back and forth. That was my other approach. Maybe we could catalog what swaps we've already made and attempt other ones. I don't know. It just doesn't seem like a great idea. So I think this solution works. Well, I know it works because we passed the test. Let's see if we've got where we kind of stacked up with everybody else. Probably not fast at all. We'll check specifically day 5. Yeah, first 100 users for both stars in 55 seconds. Like, what are these people doing with their lives? Sheesh. I suppose they probably have some sort of like auto pooling mechanism. That's kind of impressive. All right, so here we are. Day 5 is complete. Hope you all enjoyed it. If you have any questions or would like to see something else, please leave a comment. But thank you. Y'all have a good night. Bye.